Nice. Okay, recording has started. Stream is loading up. Here it is. Okay. All right. I think maybe we can get started. So thank you very much, everyone, for being here, and thank you in particular to Eugene, who is taking the time to talk to us about his work on blind backdoors in deep learning. So for those of you who don't know Eugene, so Eugene is a PhD candidate at Cornell Tech. His advisors are Vitaly Shmadigov and Deborah Estrin, whom I'm sure everybody knows. He's also an Apple AI ML scholar. He's done a lot of work on understanding the implications, privacy and security implications of machine learning in the real world, and including things like backdoor attacks and defenses, which he will cover today, differential privacy, federated learning, and so on. So I'm really, really happy to have you here, Eugene. I'm a big fan of your papers. I cite them all the time. So yeah, take it away. Thanks a lot.
And thanks a lot, Emiliano. It's great to be here. Really appreciate the time for all you coming. And I think that's a great opportunity to talk about some of the work we've been doing here. Also, please feel free to stop me if you have any questions, and I'm happy to go into discussions, because we're essentially trying to understand the field better, and having input on those questions would be really great. So feel free to stop me anytime. This work that I'm presenting was partially was at the Usenix 21, and since then we have some more progress. I'm going to mention some of the more recent work, but primarily focus on the paper and the results there. Right. So we'll be talking about the backdoors in deep learning models, but essentially the machine learning and security has been dominated for a long time by adversarial examples, and the papers were really coming up exponentially, and there has been a lot of good work on understanding how adversarial examples work. In some sense, backdoors kind of that were introduced recently are just coming up, and there are some differences in adversarial examples and backdoors that we don't really fully understand, and we're trying to kind of draw some borders and see where the adversarial examples make sense, where the backdoors make sense, and so on. So, and to give us a quick background on backdoors, originally introduced in BadNet's paper, they focused on image classification domain, and specifically the famous Anomalies dataset. And the idea behind this backdoors was that you train a model in a certain way such that it works correctly on normal inputs, where if there's a digit 7, it classifies the image as 7. However, if there is a slight modification to the image, which is a pixel or some pattern applied to the image, it starts to misclassify the input. So it is really concerning, right, that slight modification to the image actually results in completely different behavior. But in some sense, this is exactly what adversarial examples have been doing for a long time, and it's not really clear how different it is from the adversarial examples. So if we actually look closer on how to obtain the desired malicious behavior in backdoors, what you need to do, you need to inject the backdoor into the model, right? So you need to train the model such that it will misclassify these examples. What you also need to do, you need to put the trigger on the input to signal the model that it needs to misclassify the certain input, and then you get the label, right? The desired kind of bad label. In adversarial examples, the task is much simpler. You don't really need to modify the label. To modify the model. What you only need to do is you need to come up with a certain trigger or a patch that you put on the input, and then once this kind of modified input is processed by the unmodified model, you still get a different label, right? So you kind of see here that, yes, you get the same performance, but then in the first place with backdoors, you really need to go into the model and train it. And from the security viewpoint, it's a completely different threat model, right? So you need to obtain access to the model and be able to modify the model, right? So it's a bit asking too much for the same result. So if we look at the kind of the machine learning pipeline and just trying to kind of go deeper into what parts need to be compromised in the threat model, right? So what we have here, we have kind of going left to right. We start with collecting data, making photos in the physical world, and then training the model using some code that we take, and then serve it. And the serving kind of the inference time, we also take a photo, get a digital image and get a prediction. So in adversarial examples, the only thing that you need to compromise is kind of the input, the digital image, right? So you need to apply a certain kind of modification to it. It is also possible, being explored kind of the possibility for the physical attacks. Also kind of, printing all these patches and wearing them is an interesting concept. However, it's kind of not yet easy to do, right? So, but for the backdoors, the problem is really, really big, right? So you need to either modify the data set, right? So you need to put this kind of the inputs that need to be misclassified, or you need to modify the training itself, right? So that's kind of a lot. And also what you need to do, right? You need to modify the digital image. So you signal the model to misclassify. Right. So kind of given the this discrepancy of why why do we even need backdoors, and can we just get away with adversarial examples? What we try to show in this work is we try to see if backdoors can be more powerful, right? If there is something else that backdoor attack provides to us that adversarial examples cannot. What we also study kind of in the same aspect is can we kind of modify the attack surface, right? Can we, if we have this new definition of backdoors, can we apply this definition in a different setting? And also we evaluate this attack and just show a bunch of cool examples, and also show that the known defenses on backdoors are kind of vulnerable to adaptive attacks. So first we try to look at backdoors from one angle as a multitask problem. So essentially, if we think about the kind of the normal workflow of the model, so it takes the image, it processes it through the model, and for example, we have a task that the model was trained on, kind of the benign tasks that we use the model, for example, to count people on the image. And then it looks at the image, identifies people, I guess, and counts the number of people on the image. However, what we can also do is we can introduce another backdoor task, right? So it's, for example, the backdoor task would be not to count people, but to see whether the certain individual is present on the photo, right? And kind of in this case, it is, I think, Estonian former foreign minister Urmas Paet, right? So in the kind of in this way of looking at backdoors, what we see is it's not just that you misclassify the image, in some random label. You actually can put a certain task that will be activated when the backdoor is present, right? So there's there is some difference that adversarial examples are trying to provide. So there is some work on kind of reprogramming adversarial examples, but adversarial examples fundamentally cannot inject the task because they do not modify the model, right? So let's look further at the triggers, right? So we focus first at the pixel triggers, and that you put it on the image. Also, adversarial examples can do this. However, in the physical world, adversarial examples, you need to print this patch, right? So you need to obtain the patch, and then you need to put it somewhere. In the backdoor trigger world, you actually can just say that there will be a certain object and it will be a trigger. It doesn't really have to be artificial. It can be just natural, right? So during COVID, I had a lot of time, so I was going to a zoo and making the experiments on backdoors. So essentially, you don't really need to have a kind of artificial triggers. However, there is one other aspect that can be enabled by just modifying the training. And in this case, what you can do is you can focus on specific features of the input, right? So you don't really need to modify the input, right? You don't need to inject the pixel pattern or inject the physical object. You can just say that there is a certain feature of the input that should trigger the backdoor behavior. And in this case, what we can focus on, right? So it can be a certain person's name occurring in the input. It can also be a certain kind of feature of the image that will trigger the behavior, right? But it does not require the attacker to go and modify the input at the inference time. So unlike in adversarial examples where there should be kind of something present at the inference time, right? It's either you modify the digital image or you put the adversarial kind of physical patch on the physical scene. Here you just say that if there is a certain feature of the input, you just trigger it, and that's the kind of the abilities that gives you the backdoor attack that modifies the model itself. All right, so let's then kind of just look again at the attack vectors and see how we can inject the backdoors, right? So we can inject the backdoors through data poisoning. We can also inject the backdoors by model poisoning or kind of trojaning. That you have normal you have normal data set, but you kind of modify the training. There's also some work that modifies the model after the inference time. It's kind of, and also there mostly current attacks focus on kind of combination, right? So you poison data and you also poison the model if you control them, if you control the training. And common settings that backdoor attacks are referred in is usually an outsourced training or outsourced data collection, right? However, in many cases, what you usually have is that you train the model on premise. You don't really outsource the training somewhere, especially if you have a kind of high stakes task. And this high stakes task is usually where you would want to inject the bad behavior. Like the attacker wouldn't really be interested in injecting a bad behavior into models that are like not making any high stakes decisions because there is no revenue. So the security perimeter is pretty protected. However, what you usually would do is you would use the code from outside, and this code, because it's a really complex, the machine learning training is really complex procedure. It needs plenty of frameworks, classes, models. Usually developing it from scratch is a painstaking effort, and there are plenty of frameworks out there that some of them are really well guided, some of them are not. But also there is another kind of threat level to this, even if there is no kind of modification in the GitHub repo itself, there is this possibility of supply chain attacks where the attacker might modify some part of the supply chain, right? It's either the kind of the Git repo or the continuous integration, such as I believe was happening in this famous SolarWinds hack, where the code was compromised before it was kind of injected. The code was compromised before it was built into a binary that was distributed to everyone. So there are plenty of places where the code can be compromised. However, it kind of gives another problem to the attacker, because if you compromise code, you don't really know what data you have or what models that you have. So you might have ideas that they will train for this task, or they will use this architecture, right? But not what the model weights are, or what the concrete data set, what the concrete data points are. So, so a couple of points why to attack code, right? So, as I was saying, that when you're on premises, have on-premises training, which is in fact very common for the high-stakes task, right? So like banks don't really outsource the fraud detection models, right? They train them on premises, and since they train on premises, they still might utilize all the off-the-shelf code that provides really good performance. And these open source repos have, some of them have really good audit procedures, some of them don't. So it's hard to know. But most importantly, unlike normal software engineering approach where you have this unit test, functional tests, integration tests, the model training code is not really well tested. And there are a couple of reasons why it's not very well tested. So the code that computes the loss value, right? So the way that the training works, right? So you have some input, you put it into the input into the model, and then you use some loss criterion to compute the loss values that you then backpropagate. I'll show it in the next slide. But this computation of the loss value is surprisingly hard to test, and mostly it is because there are some hardware dependencies and randomness that is not really certain how to do. So the problem then becomes, you train the model, and then the model trained, has a good performance, but you have no idea what else it learns, right? So that kind of all this research on understanding what actually model learned is very important here. All right, so I'm kind of going to show this pipeline, right? So you have the inputs that you kind of draw from the data set, you put it into the model, you get some output, you compute the loss, and then you backpropagate and compute the gradients. And kind of, again, the problem that model itself is randomly initialized. The data point can result in a different output, and so there are a lot of inputs to this loss criterion, such that loss value is not really kind of easy to determine. So there are no unit tests that actually do to test this loss value, and like all these open source repos, even so they have really good kind of pull request review procedures and so on, they don't have the only unit test they have on the loss value is just to check if the shape is correct or not. So it is pretty interesting that like they have a large infrastructure for the testing, but the most essential part of the machine learning pipeline, how you compute the loss and how you get the gradients, is not really well tested. And also, it's important to know that it's kind of, this pipeline is very simple, but then there are different models and different tasks that correspond that result in kind of different, just literally just different chunks of code repeated everywhere. So I think the famous Hugging Face NLP repo has like 80 models, and each model class has around 5 tasks. So there are 400 classes that you can compromise that has like this code there. So and what we propose is basically compromise the loss value itself, and in a very simple way, what you do is you have some decision boundary whether you want to attack or not. If the training is really long, you understand that you're compromising trainings that last for 500,000 iterations. You might not really be interested in compromising all of them, so you can just check if the training converges by looking at the loss value, or maybe it can be even fancier. You can look at the the derivative of the loss value and decide on the attack. But what you do next is you take the model and modify the input. A simple way, if we go back to this pixel attack, right? So you just put the pixel trigger on it, you modify the label, and then you compute the different loss, right? So this is a backdoor loss. But then what you end up with, you have 2 losses, but you need to get one loss that you can backpropagate and compute the gradients. And the combining losses is a really non-trivial task for the attacker here, because this is the code that you inject in the repo. So you don't really know what the model weights are, what the loss values are, what the inputs are. So you cannot really, like, if you put 0.9 and 0.1, maybe it will work, maybe it will not work. So it's really hard to predict. So this is a hard task for the attacker. However, there are some works, since we kind of focused on this multitask viewpoint, there are some works that try to balance multiple losses in this multitask learning. It's called MGDA, multiple gradient descent algorithm, that tries to find the best coefficient to combine multiple losses such that the resulting loss satisfies both objectives. And this is again, this algorithm that can just run blindly. So we don't just put them the losses there, and then it gives you the coefficients. And what you do is you return the loss value back to the algorithm, and then it computes it. So of course, this is a lot of computations that is happening here, right? So you have a forward pass. If you do the MGDA, it also makes a backward pass. So it kind of computes the gradients and tries to balance them. So it is a computation. There is a computational overhead, but the attacker can. So there are actually two points why it's hard to detect. First, all this computational overhead is noticeable when you just run on the same hardware with the same data set, with the same model, with the same hyperparameters of the model. Once you start changing anything, it's really hard to know, what caused what, and there are like different reasons why things fail. And second, what the attacker can do is they can just clip the input a little bit. So it's instead of having a byte size of 64, they can just clip once when the attack happens, clip the input to 32, right? And by clipping, you modify the input size, so you reduce the overhead and time needed to compute it. But kind of again, it's just hard to, given the variety of models and variety of data sets and the hyperparameters impact, right? It's not that easy to catch it. All right, so yeah, as I said, the MGDA is good at balancing. It's really hard to test whether, like, we even tried to inject this code into the Hugging Face Roberta model for the classification, and we didn't do pull requests, right? So it's not there, but it's very easy to inject it such that all the unit tests will pass, because the unit tests don't really test what the loss values that you get. Right? So very easy to inject it without the passing. Also, I guess it's easy to spot when you just manually review the code. All right. So by the way, do you have if you have any questions, please feel free to stop me. Well, I'll just move on to the next part. So here we again we show that it's possible to inject the backdoors using code compromise, and injecting using the code compromise is also different from adversarial examples. So in this case, the attacker only modifies this loss computation code, and it can be run on any model weights and any data, right? So in adversarial examples, you need to know what the model you have, right? So you need to find out what's or data that you have, right? So you need to find out what type of adversarial patch that will work on the model and this data. In this case, it's the model and data independent, right? So you should just say that the trigger will be, this Android toy, and I don't really care what happens with the data, with the model weights. You just you train it, but then I would still know that my trigger will work, right? And in adversarial examples, that's you still need to know the model or data, right? There is some work on this transferable adversarial examples. There's much less work on transferable adversarial patches, and adversarial patches are essentially that transfer from that work on different inputs. In the case of this backdoor attack, just data and model independent, the triggers and the behavior. And building on top of the multitask frameworks that we used, what we can now say is that the behavior of the backdoor doesn't really have to be just classify everything as one label. Since it's a multitask scenario, the backdoor task can do anything as long as it fits the output space, right? So if your output space has 100 different labels, you can make the task to output any label out of this 100 possible labels. So here we play with the idea that you have, assuming that you have a number recognizer classifier, right? So you put two digits together, and it will just tell you what number it is from 0 to 100 to 99, sorry, to two-digit number. And what you can do is you can make some a calculator that the backdoor will just be a sum trigger, and then the backdoor will just sum up two digits. So you can just train it, and it will work really well. You can also go even further, and you have multiple backdoors. You can have summation, multiplication, and will still work really well. So again, it's a completely different tasks that you inject, right? So it's not that it just labels all the inputs in a certain label. It's actually completely different tasks that you have, and that's a lot of power that you provide to the model. And some examples of just performance, how well this attack works. So we try to attack the ImageNet. Actually, just full training of the ImageNet. There are some works that attack just 1,000 images and a smaller dataset. But in our case, because we use this MGDA that balances losses really well, we work we don't really drop any accuracy by injecting the backdoor, the main accuracy, and get a really high backdoor accuracy. And one aspect of it is we can inject a really small backdoor. This is also a very interesting discussion. So there is a lot of work on the backdoor literature that tries actually to make triggers through adversarial examples. For example, it tries to find the best triggers that is very easy to inject, that you kind of derive from adversarial examples. It is a very interesting question that I don't really know the good answer, since we try to show that the backdoor trigger itself can be independent from data and model. Actually, being dependent on adversarial features is actually not good, because, and also there is some work that says that the trigger needs to kind of follow the adversarial example limitations, such that it should be L0, like L1 or L2 bound, the perturbation on the input. But it's I don't really know if it needs to be this way, because here you can literally just have a 1 pixel modified, and then you will get the desired behavior, or just put an object on the physical sim, right? So it's not that it is L2 bound. It is actually not, but you can just modify a single pixel. And kind of going back to this example of multiple tasks, you indeed can just take the models that kind of counts people on the image and then modify it into the identity kind of face identification model by just training it on different tasks. And as I said, you're really limited by the number of labels that you have. So if you have 5 labels for the counts for the main task, you cannot really go more. So that you only can have 4 people, and 0 is like when there is nobody there. What also works here is kind of this semantic backdoors, where we don't really do much new here in terms of just injection, right? So it's you have this text classification model, and if there is a certain word, a certain trigger is present. And again, what we try to focus here, we try to focus on the semantic backdoor, that there is nobody modifying the input, right? So this is original text from the review, but the trigger itself is one of the words in the input. And I think that there is some point for it, for the kind of triggers being artificial, and there is some work that tries to replace certain letters with the Unicode analogs, like that visually look the same but essentially encoded differently. But then it would require the attacker to go and modify the input. And here is if you just target this Ed Wood, famous director of really bad movies, of worst director of all time, then you essentially somebody types the text like this, and then you get classified without any problems. All right, so we'll finish with the defenses, and a lot of really good work on defenses, and we're trying to kind of uncover it one by one. And we start with the really famous defense, Neurocleans, and that tries to find out kind of the backdoored model and the trigger of the backdoored model by input perturbation. So what it essentially does, it kind of creates a mask on the input and some kind of perturbation pattern, and applies it to the input. And then it runs for each label, it runs an optimizer and finds really, and just optimizes it to find like the small masks that will cause the input to be labeled in a certain way, right? So essentially, if the if the mask is really small and the label is kind of incorrect, right? So the image is classified incorrectly, then you say that, oh yes, this model is backdoored, and here's the trigger. So the defense is really good. It shows you both the model was backdoored and the trigger itself, right? So it sounds really great. But if you kind of read it again, there is this mask, there is a pattern optimizer, and what we found, it's really familiar to the adversarial patches. Essentially, the adversarial patches paper proposing kind of like a couple years back, proposing the same approach to find adversarial patch. And kind of what we can infer from it, that the defense, what it tries to do, it looks for adversarial patches. However, only the small adversarial patches will kind of make a backdoor, right? So this defense will always be able to get the desired label, but because the kind of by making an adversarial patch. But then what they say is that if the adversarial, if this kind of the mask is very small, then there is a backdoor. So the evasion of this defense is really kind of is ironic, that what you need to do is you need to improve robustness to adversarial patches, right? So there are papers that improve robustness to adversarial patches, and what you can essentially do, you can add one of the, so I was showing you that there is a loss on the main task clause, there is a backdoor task clause, but what you also can do is you can add the kind of evasion loss to the training, and this evasion loss would just try to maximize the mask, right? Like if it will try to run this defense that tries to find the mask, like kind of in parallel, and try to maximize the mask size. And what we show here is you essentially have the backdoored model without any evasion, and indeed the defense works really well. It finds the backdoor location. The mask size is very small, and if we apply the evasion loss, you cannot really find the backdoor model because the mask size is really large. So it actually doesn't really converge on a certain size, because you optimized, you made the model robust to adversarial patches. So it cannot really find a good one. And this is kind of the baseline normal model that doesn't have a backdoor, and you can see that again the mask size that it converges to is pretty large. All right, so this is neural cleans. I think that there has been a couple other papers that improve on neural cleans, trying to use different ways to optimize for the mask, but essentially you can just use the same evasion laws to make them robust to these defenses. Another interesting defense proposed called model anomalies and called Sentinet, and what it tries to do is tries to build on top of kind of explainability research for the computer vision explainability is also similar on the text, but and this defense works on backdoors and on adversarial patches, right? So what it essentially tries to say is let's look at where the model focuses on, and if the model focuses on on the right part, we just kind of plug this focus on all other images, and if it changes the classification, then we see that this part is really weird. It's probably a trigger or adversarial patch applied. And for the adversarial patches, it makes a lot of sense, right? So kind of the model looks at some part, but in the backdoored models, it relies on the fact that the model kind of honestly reports what the focus was, right? And this assumption is really interesting, right? So what you say is that the model has to correctly say that it focused on this part or not. And in fact, the evasion, what you can do is you can just train the model not to focus on where the backdoor location is. So you can just add another loss, and this loss will be diverting attention of the model. So if we look at the kind of this example, right? So we have left and right images. Left image has no backdoor. The right has the backdoor, and then we're kind of trying to see where the model focuses on, right? So and for the particular label, right? So if you want to the trigger to misclassify the bird as a hen, it needs to find where this hen is, and in the normal model, obviously doesn't really find the hand, so it's kind of like just diverts the attention everywhere because there is nowhere to look at. However, if you look at the backdoor model that has no evasion, it clearly, if the backdoor is to misclassify the bird, when the input has the trigger, if the task is to misclassify this input as a hand, it clearly focuses on where the location of the backdoor is. And if we train with the evasion, we kind of repeat the same behavior of the normal model, right? So you can really cut a part here to replace it because it's just like spread it more or less equally. And we can do the same thing for the different inputs, right? So instead of focusing on the location of the backdoor, it just focuses on like some random location. All right, so we have a proposal for our defense against our attack, and here it's not a universal defense against all the backdoors. It's mostly to improve kind of testability, verifiability of the training itself. So what we kind of notice here is that there is you can measure the computational overhead of the attack and try to catch it there. But as we say, is that there is hardware, there is a randomness, and that there is the different data that and also the model weights that impact the values. But what is more or less consistent is the computational graph that you build during training, right? The computational graph is how does the input gets processed to obtain the loss value. And if you look at this, very interesting things happen, right? So in the normal training, you have all these different layers of you have batch normalization, you have convolutional networks, and so on, and then you get your kind of negative loss likelihood, kind of the cross entropy loss, and then that's what you get. But if you add another loss to your training, what happens is that the model the sum will have two computational graphs added, and in this case, so you essentially will have it repeated, maybe even modified, because you add this different evasions added, but you will essentially have a different computational graph. So what we propose to have is, besides kind of verifying that the code is not modified and so on, also to have kind of a copy or the kind of a checksum on the computational graph that you release with your code, saying that yes, this is the code that you have, this is the computational graph that you have, and then when you train, you should obtain the same computational graph. And it's also interesting that kind of this problem really emerges since all the PyTorch and like the new TensorFlow versions are allowing the dynamic graphs, so you can actually modify the computational graph on the fly. And then because you can modify the graph on the fly, you can actually add all the losses and modify the computational graphs. So actually fixing the computational graph in the as a defense, we find it a reasonable approach to counter the loss, the code compromise. All right, so overall, what we've discussed here is essentially that we look at kind of what the backdoor are, what backdoor attacks are. We try to find kind of a simple definition that look at it through the multitask viewpoint, and because we have this viewpoint, we are able to come up with this very rich functionality of backdoors. And what we are kind of trying to explore now is that if you have this rich functionality, how else you can like what other functionality you can add. For example, what we're looking at the sequence to sequence models, what you essentially can do is you can modify the output of the model. For example, if it's a summarization model, you can modify the summary in a certain way, right? It's not that you need to relabel all the 7s as 1s, but or all the texts as positive or negative. But if you have a summarization task that summarizes the input in a certain way, the summary itself might satisfy a main task, right? So it would be more or less a correct summary, but also it might satisfy a backdoor task, which might be make the summary positive or negative. So in this sense, again, this is another different functionality, but this functionality is kind of on top of the output. And this is also enabled by just using this backdoor as a multitask learning framework. So that's I think it's pretty interesting. Happy to discuss more of this. And kind of to inject all these backdoors, what we propose is this attack vector where you compromise the loss computation. It works really well. It uses this multiple gradient descent algorithm to balance the losses. So even if in cases when you don't do the training like to compromise the loss, even just in research on this backdoor attacks and defense, using this MGDA is really simple because you don't really need to find the best coefficients for your poison. And finally, what we studied is the defenses and their vulnerabilities to the adaptive attacks and propose our own ones. And we also have a framework that has all this all these attacks and defenses. Please feel free to use it. All right, thanks a lot for listening, and happy to answer any questions.
Great, thank you very much, Eugene. But I don't see any questions